Section 7.6 and 7 are solving differential equations, which means finding either general or particular solutions. Both of them use separation of variables, and then particular solutions use initial conditions. So all of this is related. Okay, so we are going to determine general solutions and particular solutions to differential equations. As a refresher, an equation that involves a derivative, frequently this has implicit differentiation in it, is called a differential equation. Okay, we know that. And so we are going to go through and do some examples of solving it using what is called separation of variables. So really what this means is we need to get all of the y stuff on one side with the dy, and then all of the x stuff on the other side with the dx. Also anything that's like a constant or whatever, get that on the x side if possible, okay, like a coefficient. And then we are going to undo the derivative, meaning we are going to integrate, okay? As a reminder, if I said that, that I was integrating, I don't know, let's say 5x cubed dx or something like that, what I'm really doing is, and then I end up with a function and say y equals 5 fourths x to the fourth plus c. What I'm really doing is over here, I don't have it, but there's a dy, and when I take the antiderivative of 1 with respect to y, I end up with just a y, okay? So we've been doing this process, we just haven't called them differential equations. All right, so this part should be familiar because we had this problem before when we were modeling. It says, write the equation of a function whose slope at any point is twice its x-coordinate. Well, we start with the differential equation because it says whose slope at any point, okay? Well, the slope is the derivative, so this means dy over dx equals twice the x-coordinate, so 2x. Okay, the separation of variables part comes when we split these two. Essentially what I'm going to do is multiply both sides by dx to move this over here and write it as dy equals 2x dx. And then to undo those differentials, we're going to integrate both sides of the equation. So I'm going to integrate the left with respect to y because the dy tells me that this is the derivative with respect to y, and then integrate the right with respect to x. So the integral of, and then the coefficient here is just a 1, the integral of 1 with respect to y, let's come over here, would be just y. Now, you might be saying, okay, really it should be y plus c. Let's go ahead and write that for a second and see what happens. And that's a constant. Then on the right side, the integral of 2x is x squared. Now, if I write plus c, are these two constants the same? No, because they can represent any constant, so really I should call that c1 and c2, okay? And then the very next thing I would always do, because I want to write the function, okay? In other words, I want to solve for y if possible, is I'm going to get rid of this. So I'm going to have y equals x squared plus, and then if I take a constant, representing any constant, subtract any constant, I get not 0 because they're not the same constant, I get still a constant. So really when we do the separation of variables, when we do the antiderivative step, we pretty much never write the plus c on this side. Not because we don't need it, but because the very next thing is always c2 minus c1, which is just a c anyway. Okay, now this is called a general solution. All right, this essentially represents the family of functions that satisfy this differential equation. Okay, so if we think about on a graph, y equals x squared plus a constant is just this parabola y equals x squared, but we could shift it up or down however we wanted because of that plus c. This represents all of those possible functions, or that family of functions, okay? The second part says find a particular solution. So now we want to know, okay, but which one of these? So find the specific function where y equals 2 and x equals 1. So now I have what's called the initial condition, and that's this ordered pair, which we can either write as -1 comma 2, or with differential equations, it is more likely that you see it written like this, y of 2 equals, just kidding, back up. It's more likely that you see it y of -1 equals 2. So the function of -1, like at x equals -1, is 2. So this is function notation. It's just using a y instead of an f. All right, either way, we have an ordered pair, and we know that this function has to pass through that point. So I'm going to plug my ordered pair into my general solution. 2 equals -1 squared plus c. So that's a 1 plus c, so that means c equals 1. So now I know my function is, my particular solution is y equals x squared plus 1. This is the function from this family that satisfies the initial condition. Okay? All right, so that's solving differential equations. So let's try a couple more examples. If you want to pause and try them, you're welcome to do so. I'm going to erase this just to give me a little more room. Okay, might have to do some rearranging first. In this case, y prime, or dy over dx, okay, I like to go ahead and start with the Leibniz notation since we have to separate the variables anyway. It's written implicitly. That's okay, but again, I need to get all of the y stuff on one side and then everything else on the other side. So I'm going to multiply both sides by y squared and by dx. So I get y squared dy equals the quantity 8x plus 1 times dx. Those parentheses matter, okay? If I was like multiplying and then I was subtracting 1 or adding 1 or something like that, then I would not be able to integrate it, okay? So I do need to have this entire expression multiplied by dx to solve. All right, so then let's use this color. We integrate both sides. The antiderivative of y squared dy would be 1/3 y cubed. Again, I don't need the plus c over here because I'm going to put it on the right. Don't forget it though, okay? And then over here, my antiderivative is 4x squared plus x plus c, okay? Now I want to solve for y, so I'm going to multiply both sides by 3. Again, I'm going to come over here. So I get y cubed equals 12x squared plus 3x plus, now this is any constant multiplied by 3 can still be any constant. So I'm just going to leave this as c. If you put a 3c there, it would not be wrong. You're not going to see that on a multiple choice answer anywhere though. You're just going to have a constant. Okay. So from here, we need to solve for y, meaning we need to take the cube root of both sides. So y equals the cube root of the entire expression, 12x squared plus 3x plus c. Okay, now something I want to warn you of right here, this is the kind of thing where we frequently forget about the plus c until the very end. Like we forget to write it here, and then we would end up with, I'll undo this in a second, we would end up with this, and then we would end up with this, and then we would say, oh, let me get rid of that. Then we'd say, oh yeah, we need a plus c. Is that the same function as this? I know you said, yes, you're correct. It is not the same function, okay? So please make sure that if you get to the end and realize you forgot a plus c, because here's something, this c changes things horizontally, okay? Something else has to happen with that c. You need to go back to this step right here and add it and then see what happens, okay? All right, so that's our general solution. Here it doesn't say we have an initial condition, so we're not looking for a particular solution. All right, here's another one. Again, solving the differential equations. We're looking for a general solution because we don't have an initial condition. We don't have an ordered pair. So I'm going to multiply both sides by cosine y and by dx. So I get cosine y dy equals 4x cubed dx. Okay, then I'm going to integrate both sides. Antiderivative of cosine y with respect to y is sine y, again, plus c, but we don't need it. And then antiderivative of 4x cubed is x to the 4th. This is where we put the plus c, okay? And then to solve for y, I need to undo the sign, meaning essentially I'm taking the arc sign of both sides. So I get that y is equal to the arc sign of the whole quantity x to the 4th plus c. Again, this is an example where if we forgot about the x, and had this and then said, oh yeah, we need a plus c, we would have a different function. So please make sure that you have that plus c as soon as you take the antiderivative. Okay. All right. Another example here, find a particular solution containing 2, 4. So now we have an initial condition and we have our differential equation. So we're going to solve for the general solution and then plug 2, 4 in. Okay. So I'm dividing both sides by y squared, multiplying by dx. So I'm going to write that as 1 over, actually, I'm going to write it as y to the -2nd dy, since I'm going to use power rule to integrate, equals x dx. Okay, and then I'm going to take the antiderivative of both sides. Antiderivative of y to the negative second would be negative y to the negative first. Antiderivative of x would be 1/2 x squared plus c. Okay, now I have an option. Because I'm looking for the particular solution, I can plug in the 2 and the 4 right now and solve for c, or I could rearrange, isolate the y, solve for c, then plug it back in, okay? It doesn't really matter, but I will tell you that the algebra is a little bit messier if you are using multiple variables, like not just a c, but an x and a y, as opposed to just using all constants except for a c, okay? So my suggestion for ease would be to plug 2, 4 in right now, okay? So that's going to give me negative, and y to the negative first is the same thing as 1 over y. So that's negative 1 over 4 equals 1/2 times 2 squared plus c. Okay, so this is, reduce that to just be a 2. Okay, and then I'm going to subtract 2 from both sides. So I have negative 1/4 minus 8/4, which is negative 9/4. And that is my c value. Okay, then when I plug that back in, I have negative 1 over y equals 1/2 x squared minus 9/4. Okay, now I do still have to do some algebra. There's no operation that's called like reciprocate. I can't just take these and say, oh, there's 3 fractions, let's flip them all over, okay? What I can do, though, is I know that as long as none of these are 0, if a over b is equal to c over d, then that means b over a equals d over c. So as long as I flip the entire things over, I haven't broken any rules of algebra. Essentially, it'd be like multiplying both sides by y and dividing by this whole thing. I am going to divide by negative 1 just to change all those signs and get rid of that negative there. Okay, so then I'm going to have y equals 1 over this entire thing, negative 1/2 x squared plus 9/4. And then lastly, I'm going to multiply to get rid of the complex fractions. I'm going to multiply by 4 over 4 and get y equals 4 over negative 2x squared, sorry. Negative 2x squared plus 9. And then that is my particular solution. Okay? And by the way, if you partially solve this, like let's say we multiplied everything by negative 2 just to get rid of that, but then you left this as a c, you would have a different value for c, and that's okay because c just represents any constant. Once you have plugged in the ordered pair, though, that c value gets locked, and you can't, like 2 times c, once you've already plugged in x and y, has to be 2c, okay? So just be mindful of that, or let me know if it doesn't make sense and I can give you another example. Okay, one more here. I'm given the initial condition y of 0 equals 1, so this is the ordered pair 0, 1. We're looking for the particular solution of this. So I do have some rearranging to do. I want dy to stay in my numerator, okay, because it's dy over dx. So I'm going to subtract this first and then divide by this on both sides. So I'm going to have, I'll do that in 2 steps. I'll have e to the negative x squared times y squared minus 1 dy equals negative xy dx. And then I'm going to divide both sides by this. I'm also going to divide by y because I want to get that back to the other side. Okay, so dividing everything by e to the negative x squared and a y, I get y squared minus 1 all over y times dy equals, okay, this right here, e to the negative x squared, if I divide by that, it becomes multiplying by e to the positive x squared. Okay, so 1 over e to the negative x squared is e to the positive x squared. So I end up with negative x times e to the positive x squared dx. Okay, and then I am going to simplify on the left side. I'm going to go ahead and divide this. Y squared minus 1 all over y is the same thing as y minus 1 over y dy. Okay, now I'm going to integrate both sides of my equation. So antiderivative of y minus 1 over y would be 1/2 y squared minus the natural log of the absolute value of y. And then antiderivative over here, this is a u substitution problem, okay? I have that u, my inside of the composition, is x squared. So then du is 2x dx. I have the x and a negative, so I'm going to multiply by -2 on the inside, -1/2 on the outside. So this becomes -1/2 times the antiderivative of e to the u is e to the u. So I've got e to the x squared plus c. And at this step, I'm going to plug in my ordered pair, 0, 1. So I have, also I think this might be towards the bottom of the page, so apologies if you run out of room. Okay, so I have 1/2 times 1, so 1/2 minus natural log of 1, which is, we know that to be 0. Okay, so that's going to be 0, that disappears. And then -1/2 times e to the 0 is 1 plus c. So I have 1/2 equals -1/2 plus c, meaning that c is +1. Plugging that back in up here, I get 1/2 y squared minus the natural log of the absolute value of y equals -1/2 e to the x squared plus 1. Okay, we are not going to try and solve that for y, okay? There are going to be some problems that you get to and you're like, I've solved it, isolating y, more algebra than I want to do, or maybe than I know how to do, or than is even possible. So if that's the case, like, and the way that I know is that this has a polynomial piece and it has a natural log piece. There's no way to get that y out of there. So just stop here, okay?